Hi everyone, my name is Christos Soteriou. I'm Associate Professor at the EECE Department of the University of Thessaly, and it's a great honor and privilege to present our work on ASTA today in this TAU 2021 keynote entitled ASTA for Cyclic and Asynchronous Circuits. This is the presentation outline. I will start by briefly describing static timing analysis. I will introduce cyclic circuits, the motivation behind this work, and pitfalls with using conventional STA. I will then review the ASTA flow requirements. I will show an example ASTA methodology, and then I will present results on both cyclic and asynchronous control circuits, the more complex counterpart of cyclic circuits. I will then move on to discussing gate-level simulation accuracy when loops are broken, and we'll review bundled data asynchronous circuits, an easy implementation paradigm of asynchronous circuits, and eventually close the presentation with presenting the key takeaways and conclusions. So what is static timing analysis? Static timing analysis is the cornerstone in modern EDA flows. It is orthogonal to dynamic simulation. It has to be very, very fast. It supports validating all the different circuit timing constraints, including setup, hold, pulse width, recovery, and removal. And it has to support multiple modes and multiple corners, reflecting the different operating conditions and PVT conditions of a chip. Delay calculation in static timing analysis takes place by considering timing arcs. In components, there are delay arcs from their inputs to their outputs, and there may also be constraint arcs to represent timing constraints such as setup, hold, recovery, and removal. In paths, there are cell arcs that represent component delays, and there are also net arcs that represent wire delays. The goal of STA is to compute the worst case or best case delay for a given timing path. This requires considering both signal directions, both rise and fall. The uniqueness property of timing arcs illustrates whether the signal direction changes through the timing arc. For example, for unate timing arc gates, such as AND gates, OR gates, or buffers, signal direction doesn't change. A rise in the input implies a rise at the output, or a fall at the input implies a fall at the output. On the other hand, negative unate timing arc gates, such as NAND, NORs, and inverter, imply that the signal direction changes. There is also a class of non-unate timing arc gates, such as exclusive OR and exclusive NOR gates, the output direction of which depends on all of the input signals timing arcs or multiple input timing arc directions. Apart from the delay calculation itself, STA's job is also to verify that all timing constraints of a circuit are satisfied. This includes setup checks, which must be performed in late analysis mode or worst case, based on the longest critical paths, and early checks or best case analysis checks, which must be performed using the shortest critical path. Additional delay checks include recovery and removal constraints, which are essentially setup and hold equivalent checks for asynchronous inputs. And for latch designs, more complex time borrowing analysis must be performed based on the latch clocks, and also pulse width analysis must satisfy that pulse width constraints for latches are not violated. In terms of industrial practices for STA, the basic components include delay lookup tables, slew lookup tables, timing constraint lookup tables, and for latest small-scale technologies where wire delays dominate, current vector lookup tables. All of these are described typically in one of many .lib formats. These include NLDM, nonlinear delay models, CCS, composite current source models, and LVF, library variation format model. The latter is essentially focused on modeling random process variations. The mentioned CCS model is particularly important for accurate modeling of wire resistances in delay calculation. A gate output in CCS is modeled as a current source through the use of lookup tables, modeling current over time. This allows for voltage over time calculations to be performed at the receiver side of what may be an arbitrary complex RC network, taking into account the presence of resistances and nonlinear capacitances at the receivers. The computed waveform is then converted to the conventional slew and delay values used by STA. GBA, or graph-based analysis, represents the most computationally efficient form of STA, where both delays and slews are upper bounded for any path and any delay computation. So for setup analysis, we always consider the dominant fastest slews, whereas for hold analysis, we always consider the best delays and the best slews. To reduce the pessimism inflicted by GBA, path-based analysis performs delay and slew computation on a path-by-path basis, considering only the delays and slews of the path. Comparing the two approaches, GBA is fast as its worst-case polynomial complexity. However, it produces pessimistic results and produces a number of false paths. By targeting specific paths, PBA can increase the accuracy, reduce the pessimism, but it cannot be applied to all of the paths of the circuit because it's worst-case exponential. Having reviewed the STA fundamentals, I will now move on to cyclic circuits, their motivation, and pitfalls. It's very interesting to observe that cyclic circuits are indeed among us. I will describe various circuit types that are used today in industry and are typically timed using SPICE-level electrical simulation. These include ring oscillator-based circuits. They may be continuous ring oscillators, stoppable ring oscillators, or ring oscillators connected to digital logic such as asynchronous counters or timed Vernier lines. Also, in neuromorphic computing and networks on chip, the network on chip interconnect circuits are typically clockless or asynchronous because of their much better efficiency and are typically based on handshakes between neurons. These may be cyclic circuits. Another well-known paradigm for implementing synchronous islands with asynchronous communication is the Gauss approach. Gauss itself is a cyclic circuit. In the Internet of Things, which is currently a big revolution, it is very important to be able to implement small, power-efficient control circuits. And these may be implemented either using ring oscillators or an asynchronous, simple asynchronous state machine. So, what is a cyclic circuit? A cyclic circuit is a circuit containing one or more combinational cycles. It may be composed of both cyclic portions and acyclic portions, and may also include sequential elements. So here you can see a circuit with a pair of latches where there is a combinational cycle between the two latches of the circuit. It may also be of arbitrary complexity, such as the larger cyclic circuits shown here. So, what is the issue with cyclic circuits and conventional STA? Well, the presence of cycles implies that the gate pin will be visited more than once by STA traversal. However, this is not supported by traditional STA, as all STA algorithms assume a directed acyclic graph representation of the circuit. So, if we consider a ring oscillator with an enable signal, the way this circuit is traversed, a conventional STA timer will detect a timing loop which is closed by this yellow timing arc. Now, the conventional timer will cut that timing arc, and from that point on will not propagate any delay or slew values from the A2 input of the NAND gate to the output Zn. And this is a fundamental problem. The slew propagation that doesn't take place will result in inaccuracy. So conventional STA tools will cut cycles either at arbitrary points or selected points, aiming for a minimum cut. I also have here an excerpt from an optimization flow manual, which says that if the circuit has timing loops, the user must break them, as the software may break them at different points as optimization progresses. Let's look at the ring oscillator test case in a little bit more detail. During slew annotation, slew values propagate through the circuit forward. They reach the output gate pin and eventually loop back into the cut timing arc. However, as the A2 to Zn timing arc is cut, that means that the Zn slew is completely independent of the slew on A2. Thus, the Zn slew and delay values are incorrect, as they're uncorrelated to the A2 to Zn timing arc. In addition, as we don't iteratively propagate the slews across the cycle, that is another source of error which we're not taking into account. So that probably means that our slews are optimistic rather than pessimistic. This error carries to the SDF. SDF files do not contain slews, but the delay values that they contain are a function of the slews in the timer. So can this STA error be mitigated? Well, expert designers use what's known as manual slew override. So this is a process where what we could do is we could manually annotate the slew on the output of the cut arc to be approximately equal to the worst case slew across pins A1 and A2. Then we would do timing analysis again, allow the slew to propagate back to the input, and we would do this again until it reaches equilibrium. As you can understand, for large circuits with many loops, this is a very tedious process. Now, what about latch designs? Latches may form arbitrary Datapath cycles. Now, in the case where latch cycles are cut, there will be an impact to STA results, as slews will not be propagated correctly, as shown in this example. Let's review a ring oscillator test case within a latch loop. Let's assume that the STA tool breaks the loop by breaking the D to Q arc of latch L1, the one highlighted in red here. The problem with this is that worst case slew will not be propagated from D to Q, but only from G to Q. So this will significantly hinder the accuracy of the STA process, as worst case slew bounding indeed will not take place. So therefore we can see that even Datapath circuits exhibit issues with cycles when these contain latch loops. The most general type of cyclic circuits are asynchronous circuits. So an asynchronous circuit is essentially a cyclic circuit implementation that may also have an explicit environment behavior, like the circuit you can see here that has a set of handshake signals on the left and the right. This is typically described using some form of event model representation, like the one you see here. This event model essentially describes all the signal changes from input to output, input of the environment to output of the circuit, output to output, and also output of the circuit and input of the environment. So essentially, it's a closed loop model that describes all permissible behavior and environment responses. So in terms of the event models used for these cyclic asynchronous circuits that describe the closed loop behavior, they're all based on a control model known as Petronet, named after its inventor. The Petronet model is a closed loop model that is able to model both concurrency and choice in the same graph, and it can be thought of as a number of composed state machines that work concurrently in one graph. In more detail, a Petronet is composed of two types of graph nodes, transitions and places. Transitions may only connect to places and places may only connect to transitions, and there's a number of so-called tokens that mark the active places similar to the active states of a state machine. When a transition fires, the transition can only fire by consuming all its input tokens and producing tokens on all of its output places. So you can see a firing example here. The right-hand side transition fires, and then the left-hand side transition fires, and we end up with one token on the left and two tokens on the right. Now, in general, we want places to possess one token to correspond to a digital circuit. And without boring you too much about the event model details for asynchronous circuits, you can see here that a simplified Petronet is often used, and that this is a marked graph. You can see down here a marked graph specification of a very simple handshaking circuit with an input handshake and an output handshake. You can see the actual Petronet on the right-hand side in its full complexity, and you can see an animation of the simulation of the Petronet in a tool called Warcraft that models concurrent system and allows you to create these event models. So, what circuits can ASTA handle? ASTA can handle both cyclic and mixed cyclic acyclic circuits, such as the one seen here. It can also handle asynchronous circuits, and these may be described as a gate-level netlist, as shown here. And there may also be coupled with an event model that describes the internal signals interaction and the interaction of the circuit and the environment. I should stress that the event model is completely optional. Our STA flow, and in the examples I'll show you later, only rely on the gate-level netlist. It is optional for the user to provide the event model that goes with it. Now, ASTA simply cannot handle circuits with shorted outputs or tri-states, as such cases violate the basic STA principles. So what about ASTA application areas? Well, we've seen various cyclic and mixed cyclic acyclic circuits that would benefit from ASTA, such as ring oscillators, ring oscillator derivatives, and more. Similarly, for asynchronous circuits, for instance, NOC interconnect nodes, latch controllers, IoT control, etc., 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 ASTA would be beneficial. Now, none of the above can currently be accurately timed because of the inaccuracies with slew propagation that I discussed earlier. And it should also be noted that ASTA is and must be independent of the circuit implementation. It should work at the level of a gate-level netlist and should be technology independent. So I'll now review some examples that I'm going to analyze later in the presentation of mixed cyclic acyclic circuits. These include the ring oscillator we saw earlier, a timed Vernier line that is often used as a voltage to time converter, and the Gauss clock controller. You can see that most of these circuits are cyclic. The only one which is on the boundary between cyclic and asynchronous is the Gauss clock controller. And in terms of asynchronous circuits, I'm showing here two examples of asynchronous circuits attached with their event models for clarity. So we can see here the first one on the left is an asynchronous latch control circuit, and it has an attached event model, and it may be used to control a latch for a pipeline or a complicated data path. And on the right-hand side, we can see an asynchronous control circuit with its attached event model. Now, in terms of top-down ASTA flow requirements, what we would like to have is an ASTA flow that can handle arbitrary cyclic, mixed cyclic, acyclic, or asynchronous control circuits. We'd also like it to have excellent correlation to industrial STA engines. We want it to be fast and accurate, so it must be GBA rather than PBA based. We would like to support CCS and multi-mode, multi-corner, just like all industrial class timers. We would like it to support false paths, incremental mode timing, derates. We would like it to strictly upper bound SPICE simulation. And we would like an efficient interface to SPICE and Verilog simulation. And lastly, we would like to be able to ultimately remove unneeded pessimism, relaxing the STA upper bound. So let's review an ASTA example methodology for asynchronous or cyclic circuits. The simplest and most fundamental ASTA flow is composed of a total of 4 steps. The inputs to the flow are the Verilog netlist, the library technology data, and any associated environment constraints of the circuit. An event model may also be input to the flow, but it's entirely optional and up to the user. So the STA flow consists of these 4 steps. The first step is the cyclic equilibrium slew computation. What that means is that we will propagate the slews across the circuit, across all cycles iteratively until they settle. In the second step, we will construct the event timing graph. This is almost identical to the timing graph for a conventional Boolean circuit, only it also contains the directions for signals. So that's the rise and fall. In the third step, we will annotate the event timing graph by delays that are computed based on the netlist. So we will annotate all delays in the timing graph from every signal to every other signal, and we call these T to T or transition to transition delays. Finally, as the event timing graph or ETG is annotated, we are ready at this point to perform period and critical cycle computation. We will now review each of the steps in detail. So in the first step, the equilibrium slew computation, essentially we compute the worst case or best case slews across all cycles. Now the slews need time to converge, so this is performed iteratively, and the process terminates while all the slews have settled within a given error margin. So for example, in the ring oscillator, which we reviewed earlier, it's important to note that the connection from the inverter back to the NAND impacts all the gate pin slews in the cyclic path. So we will let the slews settle, and then once they have settled, we will use these slew values, the equilibrium cyclic slews values, to annotate any delay values in the next steps. In the second step, the event timing graph construction, the event graph is either automatically generated from the netlist or it's generated from the event graph provided by the user. In the case where a user provides an event graph, such as the one we can see here on the bottom left, the user must associate the event model names for transitions to the inputs of the circuit. So for example, A plus must be associated to the port of the circuit because these may not necessarily have the same name. And events are also associated internally with the reachable gate pins of the netlist. So as you can see here, A is connected to 1, 2, 3 gate pins. So whenever A changes, so whenever there's an A plus or an A minus transition, these gate pins must switch. In the third step, the transition-to-transition delay derivation from the netlist, essentially we annotate all transitions in the event timing graph. The way we do this is we look at the point-to-point delays from every point of the circuit to any other point. So these are essentially loopless arcs. In an event model, we may, for example, have a path, for instance, from A plus to Y plus, or from A minus to Y minus. And in the circuit, that path, that worst case path, may actually be broken down into multiple paths, because there may be multiple paths from A rising to Y rising. In this case, what we do is we use conventional STA to compute the worst or best case path for these point-to-point or transition-to-transition delay arcs. Once we're done with this process, it means that we have completely timing annotated the event timing graph as we've computed all delays from every gate pin to any other gate pin, either in worst case or best case mode. For advanced designers, these may manually override automatically derived paths if they believe they know which path is the sensitized path. So, in the third step, we now have the event timing graph annotated, and you can see an example here where I'm showing an event model annotated with delays from the netlist. On the left-hand side, you can see the circuit. On the right-hand side, you can see the annotated delay model. However, you can see that some of the timing arcs have question marks. This is because these are output to input delays. So they correspond to delays of the environment of the circuit, as many asynchronous or clockless or cyclic circuits may have environments. So we can either fix these delays to 0, or they can be manually defined by the user using SDC commands. In the last step of the flow, we have the entire event timing graph annotated, both based on the delays internally within the circuit and based on the environment output to input timing arcs. So we're ready to then compute the period and the critical cycle. So for this very simple example I'm showing here, you can see the critical cycle illustrated on the event timing graph, and the sum of the timing arcs is 1.78 nanoseconds. So this is the critical cycle of the circuit, and it's illustrated to the user so that the user can perform changes to potentially optimize the circuit. To be able to validate the ASTA results against the golden model of SPICE level electrical simulations, we provide a SPICE level validation method. Now, this works by generating a SPICE netlist and then single stepping the simulation of the event timing graph. What does that mean? Because the circuit is cyclic, it means that events happen one after the other. So it's very hard to let SPICE run the entire circuit, because we have to let each event produce a successor event, and then based on the delay that the successor event occurs, a new input may have to arrive. So to resolve this issue and to simplify things, we do this step by step. So for each step in the event timing graph, we produce a SPICE stimulus for the inputs of the circuit. We perform transient analysis, and we measure the output arrival, again based on the SPICE simulation. So we do this step by step. Then after the output happens, we produce the next worst case inputs. And every time we do this SPICE simulation, we measure the delay or the delta between the two output events, or the occurrence of two output events. When these timing separations have settled, that means that the circuit has settled into its worst case critical cycle period. So this is a very straightforward way for measuring the period using SPICE simulations. It is also possible to derive the critical cycle, but this is harder, but it is possible by looking at the way that delays have essentially developed during the simulation. As the event timing graph model is closed, we're also able to generate a Verilog Testbench that essentially represents the environment of the circuit, so the output to input connectivity of the circuit. The way we do this is we generate always add blocks per circuit input signal transitions, for example, a signal rising and a signal falling, and these essentially represent the test bench outputs. And there's also the usual initial block for reset process, which depends on the initial state of the cyclic or asynchronous circuits. Now, if we need to essentially describe some causal relationships between the outputs in blue and the inputs in red, this is typically done as shown here. There are always blocks in the test bench where we use the pos edge and neg edge classifiers here, and then when we need to essentially say that when both of these occur, A rises, we simply use an if with a conjunction. So, having reviewed the simplest ASTA methodology and validation flows for SPICE and Verilog Testbench, I will now show some results on cyclic and then asynchronous circuits. The first cyclic circuit example that I'm going to review is the ring oscillator we saw earlier. For each of these cyclic circuits, I'm going to essentially compare three different test cases: the automatically generated ETG results, the user-defined event graph results, and the SPICE results. So when you load the circuit into the STA engine and you don't provide an event model, the ASTA engine creates its own so-called reduced ETG or RETG, which is essentially an ETG with a reduced number of timing arcs for essentially performance reasons. So on the left-hand side, you can see the ring oscillator test case. This is the extracted RETG, which is essentially on the gate pins of the circuit. And on the right-hand side, you can see the different rows, different sets of rows corresponding to the automatically extracted RETG, the designer created ETG, and the SPICE data. So you can see that the first two test cases have identical ASTA period. SPICE is faster, so ASTA effectively upper bounds SPICE. And in terms of execution time, obviously the ASTA execution time is similar for both with and without STG, and SPICE is slower as expected. The second cyclic circuit example we're going to consider is the voltage to time converter or timed Vernier line. This circuit is slightly more complicated than the ring oscillator because it's composed of both cyclic and acyclic portions, and it requires a slightly more sophisticated ASTA flow. Now, in the first step of the ASTA flow, like before, the tool will automatically create the ETG for the cyclic circuit. It will then perform ASTA critical cycle analysis as before. And then once that is done, it must propagate the delays from the cyclic portion, which is timing annotated, to the acyclic portion, so to the flip-flops, and it must also perform setup and hold slack analysis on the acyclic portion. And for this, we can use the conventional STA methods, as usual. So what I'm showing here is the cyclic portion in red, the acyclic portion in blue, and at the bottom here, I'm showing the event transitions that take place, or the event timing graph for the cyclic portion. The goal of a Vernier timing circuit is to accurately measure the offset delay between the rising edge of a start signal and the rising edge of a stop signal. The Vernier timing circuit is composed of two buffer chains, an upper buffer chain of stage delay delta 1 and a lower buffer chain of stage delay delta 2, where typically the delta 1 delay is greater than the lower chain delay. So by being able to finally calibrate the time difference between delta 2 and delta 1, we have a very fine increment of delta for measuring the relative delay. In the middle, there is a set of flip-flops that are fed essentially from the delta 2 and delta 1 buffers, and they provide a thermometer code. How does this work? We will now see the VTC operation in action. We can see here the data propagation on the top chain and the clock propagation on the bottom chain. If the clock arrives after the data, we will have a 1 propagating at the flip-flop output. However, if the clock arrives after the data input, then we will have a 0, and that gives us the thermometer code that we expect to measure the timing offset between the two signals. And at the bottom here, you can see the table of the arrival times at D and the arrival times at Q and how the thermometer code is worked out. On this slide, we see a slightly more complex version of the VTC with more stages. The green bit is the cyclic portion, the red bit is the delay offsets from the cyclic portion. We can see the period is computed as 0.77456. And ASTA can perform automatically setup analysis and measure the rise slack, fall slack, rise delay, and fall delay for all the flip-flops in the timed Vernier chain. And as expected, as we propagate down the time Vernier delay lines, the slack is constantly reducing and turning negative. We now review the ASTA results against SPICE for the smaller VTC. We see that the ASTA period is identical with an automatic ETG or without, and it essentially upper bounds SPICE. And we can also see that the setup slack is identical. That's the worst case slack of the chain. And in terms of execution time, SPICE takes about 4 seconds, whereas ASTA takes a few milliseconds. We will now review results on the Gauss basic cyclic circuit structure. The motivation is that it's difficult to distribute the clock to very large chips, so we may be able to use globally asynchronous but locally synchronous frequency voltage domains. These are called Gauss islands. And we sometimes need to communicate and synchronize between the Gauss islands, and when that happens, we use a handshake protocol. The way that works is when we get a handshake signal, then the local clock must stop to avoid any metastability issues. It's as simple as that. So there is a mutex, a mutual exclusion element arbiter that decides whether to stop the ring oscillator clock if a handshake comes in, or to continue essentially triggering the clock up and down. I will now briefly review the Gauss structure. There is a locally synchronous island driven by a DLL. And the DLL's clock period is decided by this adjustable delay element. The circuit is reset, and then the DLL will keep oscillating. Then there may be some handshaking coming in from the Gauss port, so from another IP in the same NOC. The mutex, the mutual exclusion element, will decide between the incoming request and the clock edge. It's an arbitrary select. So let's assume that the mutex grants the DLL, then we keep oscillating, and then the 1 will go around the loop and will become a 0, and we will send the clock edge to the local island, and then we will clear the mutex. And as the mutex is cleared, it will then decide to stop the clock and latch data to pass them to the local island. That's how communication takes place. The input side is acknowledged, and the data are sent to the locally synchronous island, and then the regular clock oscillation is resumed. So for the Gauss controller we just saw, on the bottom left here, you can see an event graph for its behavior. That's taken from the literature. On the right-hand side, you can see essentially the netlist with the event timing graph overlaid. And you can see that the critical cycle on the event timing graph on the left, the handcrafted user defined, is identical to the critical cycle computed by the ASTA automatic process on the right. And in terms of results, we can see that the SPICE period again is more optimistic than STA. So STA effectively upper bound SPICE. The ASTA values are identical for the automatically generated RETG or the user provided ETG. And there's also the setup slack on the flip-flop here on the data handshake channel here. And it's identical for both implementations. And in terms of execution time, in SPICE, it takes about 7 seconds, over 7 seconds. In ASTA, it takes a few milliseconds. So if I could wrap up the conclusions for cyclic circuit ASTA based on the results we've seen that ASTA is strictly upper bound SPICE simulation. It's very nice that it automatically computes setup and hold for all the flip-flops fully automatically, because computing them in SPICE is very tedious. There is no point for the designer to use an event graph to the tool, because the automated event timing graph produces identical results. And of course, the difference between the critical cycle period and SPICE depend on the lib margins and the technology library used. Now, we'll move from cyclic to asynchronous circuits, which are significantly more complex. We've shown these examples before. These are two, an asynchronous latch control circuit on the left and an asynchronous control circuit on the right, and they have their own event models. So what we've done is we've taken as many asynchronous circuit benchmarks that we could find from the asynchronous community. These are specified as event models, as we discussed earlier. We synthesized them as gate-level circuits using a tool called Petrify. Then we mapped them to a 0.25 technology library, because this was the library we also used for cyclic circuits. And then we performed ASTA and STA on them. And we contrast the ASTA critical cycle with the STA critical path. Now, there's obviously no direct correlation between the two. This is like comparing apples to oranges, but we compare them just to show how far off the STA critical path is to the true ASTA critical cycle for a circuit like this, after STA loop breaking, of course. So on this slide, we review the ASTA results versus the STA results on the asynchronous control circuits that have a lot of loops. And on the first column, we can see the design name. These are asynchronous benchmarks, the number of cells, the number of gate pins. Under the pink columns, we have the critical path delay, as reported by an industrial STA tool, the number of timing arcs disabled. And under the blue columns, we have the critical cycle delay, computed from the ASTA tool, the number of event timing graph nodes, and in the last column, we have the percentage delay difference. So you can see that even in cases with 0 disabled arcs, there's a significant difference between the critical path delay and the critical cycle delay. And on average, the percentage delay difference is slightly over 50%. So that means that it's highly dangerous to use a conventional STA tool to perform timing analysis on such circuits. Here we're also depicting the results in graphical form, where the blue line is the cyclic ASTA clock period and the red line is the STA clock period. So you can see that in all cases, the blue line is over the red line. We've also performed ASTA result correlations versus SPICE. And down here in these pyramid charts, you can see the pink pyramid is ASTA, blue is SPICE, and in all cases, the pink pyramid is above the blue pyramid, showing that we always safely upper bound SPICE, even for the largest test case, MR0. The average delay difference between SPICE and ASTA is about 15.99% for this library and for these test cases. Zooming into some interesting test cases, this is a test case here called CHU 150 where no arcs are disabled. However, the point is that the critical cycle is through the environment. So it's between the circuit and its environment. And you can see here that there is a major delta between the critical path delay. Even if you multiply the critical path delay by 2, you again don't get the same value. And this is because of cyclic slew propagation. Slews are very different. For the largest test case, MR0, you can see it has a reasonably large event graph and an even larger looking circuit that has a lot of loops. And for that, we get a 17% difference to STA. So what about gate level simulation? We have seen results of ASTA versus SPICE and ASTA versus STA. But what is the impact on gate level simulation? Because gate level simulation is often used to functionally simulate circuits, assuming that the results are always correct. So the point I'd like to make here is that gate level simulation is only as accurate as the STA engine used. So for cyclic circuits, due to the presence of loop breakers, the STA timing arc results may be incorrect. And I showed that early on in the presentation with the animation that slews are incorrect and therefore delays are incorrect and therefore the SDF will be incorrect. So that means that certain delay timing arcs may be optimistic. I have also put here for completeness, the manual slew override approach, which is used by expert designers that use cyclic or asynchronous circuits. And what they do is they follow the 6 steps. I'll review them very briefly. They identify the cut timing arcs. They measure the worst case slew at the cut timing arc input. They manually override the slew at the cut timing arc output, which, if not explicitly annotated, would otherwise be 0 from the input side. After all the cut timing arc slews have been manually overridden, they would run STA again, and they would repeat this. So this is similar to our cyclic approach. They would repeat this again and again until the slews have appeared to have settled. But then, if any change happens to the circuit, they would have to do the process again. So on this slide, I'm showing results of SDF simulation versus SPICE. And essentially, again, in the first column, we see the design, the number of cells, the ASTA period, and then the SPICE period in the blue column. And then we use an industrial STA SDF with a manual slew override. So this is essentially the best, as good as it gets for manually generated SDF versus the SDF generated automatically from the ASTA tool. So the brown column shows the STA SDF flow period with slew override. This is simulation. The orange column shows the simulation result, the simulation period with the ASTA SDF, and the last column shows the SPICE simulation time. So if we look at these numbers, the first thing we notice is that there is one test case here where the simulation with the STA SDF with the cut timing arcs does not bound SPICE. So that means we have a major timing error because we are optimistic over electrical simulation. For all other cases, this is not true, and this is essentially influenced by the fact that we used manual slew override by hand. If we didn't, we would have a lot more outliers. Another thing we can notice is that, for example, for the MMU test case, there's significant pessimism between the ASTA period and the ASTA SDF simulation flow period. And this is because there's pessimism in the ASTA critical cycle computation. Another takeaway from the table is that there is more margin between the ASTA SDF flow and SPICE rather than the STA SDF flow and SPICE. So there's a better margin using the ASTA SDF and doing simulation than there is to using the STA SDF and simulation, simply because of the timing, cut timing arcs. So the industrial SDF flow for the presented examples, just to summarize, it provides results with smaller SPICE margin than the ASTA SDF, which is highly dependent on the timing arcs disabled by STA. In the problematic test case, the STA disables arcs of the critical cycle, and this produces a result more optimistic than SPICE, and this is a major timing error. So these timing errors propagation into the rest of the circuit may lead to optimistic or pessimistic results, and these will be dependent on the circuit and the loop breakers that is decided by the STA tool. Now, on the fact that the ASTA period is more pessimistic than the actual ASTA SDF simulation, that's because of the presence of false cycles, which is similar to false paths in acyclic circuits. So we verified this carefully, and we identified that the critical cycle for the MMU test case is really a false cycle, and it is not a sensitizable cycle based on the behavior of the circuit. I will show the false cycle example in the next slide, but before I do that, I quickly wanted to review the SDF delays comparison between the STA SDF and the ASTA SDF. And you can see here, these are plotted as delay difference distributions. So you can see on the left-hand side is the rise delays of the SDF, on the right-hand side are the fall delays of the SDF. And you can see that for 18 timing arcs, there's a 6% rise delay difference. And here for about 24 timing arcs, there's 5% delay difference. So there are significant differences at various timing arcs as these arise from the cut loops. And in terms of illustrating an example of a false cycle, And in terms of the false cycle in the MMU test case that we talked about, this essentially corresponds to this worst case delay path from BI input rising to LSR out rising. And it is highlighted in this animation here. So we go through these gates and we loop back, and then we output to SLR0, and this is essentially the path that essentially closes the critical cycle when we do ASTA. However, during SPI simulation, the true path is sensitized, which is LSR on the input side, LSRI rises to LSRO rises, and this is the blue path showing here. So a false cycle is nothing but a false path which essentially closes the critical cycle for an asynchronous circuit. A special case of asynchronous circuits are bundled data circuits. So these are circuits that are composed of two parts: an asynchronous control, where latch controllers essentially decide using asynchronous circuits when latches open and close by communicating with each other via handshakes. And there's a latch data path. It also may be a flip-flop data path, which essentially performs the computation based on the opening and the closing of the latches, and there's Boolean logic between the latches as usual. What's nice about bundled data circuits is that they can automatically be derived from a synchronous circuit structure by a method known as desynchronization. So I'm showing here an original circuit, synchronous circuit pipeline. I can simply remove the clock. I can replace each flip-flop by its own internal latches. I can then use delay elements to track the combinational cloud delays. And I have these clock generators that are essentially asynchronous latch controllers that manage the data flow, and they control when my latches open and close. And I can do one better. I can also retime the circuit and split the combination logic between latches in order to improve my circuit performance. This type of circuit requires an even more sophisticated ASTA methodology, because it has this non-cyclic portion which requires standard STA. It has the cyclic portion which requires ASTA, and it also has the control buffers interface. So essentially what happens is we have generated clocks or arriving clocks from the asynchronous portion here, and then we have buffers that delay these clocks, and then we have some arrival times at the latches. And what we must ensure is that the launching path through the launching latch is always slower than the capturing path 2 through the capturing latch controller and capturing buffers. And this will ensure that we satisfy the setup constraints on the latch in the data path. So the key is to use these relative timing constraints for correct operation, and these are essentially the usual, essentially the path differences that I just described. There is no point in looking at them in significant detail, but what's important to note is that these must be verified through STA ASTA combination. So we need the hybrid. Apart from these, we must also ensure that the pulse width at the latch G outputs generated by the latch controllers and then propagated through the clock buffers meets the pulse width constraints of the latches in the library. So to summarize the bundled data STA flow, we must first perform STA for the data path portion. We must perform ASTA for the control portion. Then check the relative timing constraints. So compare the enable arrival time at the data departure, the launching side, plus the data delay STA against the capture side, the enable arrival time at the data arrival plus the setup time. And we must also perform pulse width checks for all latches in ASTA. And if the relative timing constraints are not met, then the timer can drive circuit modifications and revalidate the timing as usual. So I will now try to draw some conclusions on what we have seen and some key ASTA takeaways. The first takeaway is that ASTA works. It's possible to time cyclic and asynchronous circuits. It's essentially a superset of STA. Our results confidence is high. We compared against SPICE. What we showed here is an older technology, 0.25 micron. However, we have used other, including state-of-the-art libraries, 0.13 NAND gate and the Arizona State University 5 nanometer, which is also used for the TAU contest. We have seen that a strict upper bounding of SPICE delay is demonstrated, and ASTA is technology independent, so it's a general purpose. So we believe that it resolves STA and simulation timing errors for circuits with cycles. It improves simulation and power analysis accuracy. It can enable faster and better circuit design. It can improve advanced latch STA accuracy, something that I didn't talk in depth about. But for latch designs, it is important not to break cycles for slew propagation, as we discussed. It may be used incrementally for timing-driven operations or ECO, and it has similar computational complexity as classic STA, so it is as fast. So after the key ASTA takeaways, let's look a little bit at the vision on the flow and the work in progress. Today, what we have shown is that ASTA works, and we are able to time cyclic, mixed cyclic, and asynchronous circuits. We're also able to time latches without loop breaking, and we're also able to time bundled data circuits. Our first goal is to support all or most industry timing standards, and we're almost there. Our second goal is to work with an EDA or a semi-vendor to achieve silicon-proven ASTA results. And from then on, it's a matter of working on PBA, removing unneeded pessimism, working on reducing the margin on false paths and false cycles, and ultimately support more advanced issues that are related to more sophisticated analysis like isochronic forks, relative timing constraints, and arbitrary constraints. And this is another slide illustrating the industry adoption roadmap. As a first step, we are now at the mixed cyclic, acyclic ASTA point. The next step will be advanced latch timing ASTA, and then GBA ASTA, we're more or less there, and then PBA ASTA and advanced ASTA essentially at the end of the road. And we're not that far away from that. So I would like to now state the conclusions that conclude my talk. I believe that cyclic STA and ASTA are viable extensions of classic STA. They can help time circuits that cannot be timed today with conventional tools. That is mixed cyclic, acyclic, or asynchronous circuits. It's a great alternative to SPICE simulations. It's, of course, orders of magnitude faster. It saves the engineer from manually computing setup slack, hold slack, or other timing parameters using SPICE. ASTA is design methodology agnostic. It operates at the netlist level. It doesn't require any asynchronous knowledge or any event models, or everything is fully automated. It supports state-of-the-art timing library features like CCS and so on. It can enable, in general, faster and better circuit design. And in the long term, we'd like to partner with an EDA vendor if this ASTA technology is to be commercialized. Thank you very much.